Hello guys, welcome to my channel and first let me introduce myself. So my name is Hitesh Kumar and I am currently BTech third year in CSE from Triple IT Sonipat. So the purpose of this video is to start a kind of problem solving for DP because DP dynamic programming is one of the most important topics in CP and it can help you to take from like 1100 or 1200 on code forces to like 1600 on the most number of problems. So these problem solving will be more like towards the lead code questions as well as some code forces questions. So initially it will be for lead code questions. So we have lead code question number 62, unique paths. So what does the question say is there is a robot on an M into N grid. The robot is initially located at top left corner, that is on 0, 0, and the robot tries to move to the bottom right corner. So if we look at this, it's going to look like this is a grid. I'm not that much good on drawing part. So yeah, trying for the first time. So if it is a grid, so it is saying a robot is initially at here, kind of similar to human, and it has to reach here. This is the endpoint. What else does it say is the robot can only move either down or right at any point on time. So, say the robot is at some point here. So, what it can do is it can either go to the right or it can go down. It can never go back or up. So, these are kind of prohibited. These are not allowed for the robot. So, it can just go either left or right. Now, coming again, given the two integers m and n, return the number of possible unique paths that the robot can take to reach the bottom right corner. Yeah, that's simple. The test cases are generated so that answer will be less than or equal to 2 into 10 to the power 9. Okay, so what it's saying is, say the robot starts from somewhere here and it can follow a path like this. It can also follow a path like this. It can follow a path like this. So you can see there are multiple paths. There's no one fixed like it has to go in just one or two. There are multiple paths. Some of them are like overlapping. Say goes to this, then down, then again right, then down, then right, then down. Like kind of staircase. So there are multiple and numerous number of paths that the robot can follow, starting from here and going to the very end. So we'll be trying to drive the solution. So first let's talk about state, which is the basic starting point of DP. So we'll be using a 2D DP here since we have two parameters. We'll be using DP as ij, where I shows the x coordinate, you can say, or you can say the row, whereas j shows the column part. And the DP stores the number of unique paths till that column. Say we are talking about this is too much used. Say we are talking about this column, this one. So if we ask about like what's the dpij value of this? So it's this state gonna return the number of unique paths till this cell that we have from here, from the end. Like we are not calculating the unique path from the starting, we are calculating the unique path from the very end. It's kind of reverse of that. Now, the second thing is transition. So transition is going to be like dpij equal to the function of going right plus the number of unique ways of going down. So what it will do is it will count the number of ways or the number of unique paths of the adjacent right cell and the adjacent bottom cell. This is the transition that we have got. So this is transition state, and this is the normal state. Apart from this, now let's talk about what are the base cases. So if this is a matrix, let's add one more. Doesn't look good anyway. Okay, so if we get the value to somewhat here, and it start calling to its adjacent right, which doesn't exist. So it gonna throw an out of bound error. So for handling that, what we're gonna do is we're gonna return a value of 0 so that there is no more function calling for the right side. And the same thing goes for the bottom row as well. If we call something for the bottom down columns, then again it's gonna go out of bound. So we are going to return 0 for that. Now the base case, the ultimate base case is this intersection point. That is the endpoint of the robot where the robot is gonna reach. So here we will return 1 because there is just one way at this, there's just one unique path on the final tile. Now if we start going back towards this 0, 0 tile, we will add up all these transition states, and this will give us all the unique paths. So what we'll do is we will be starting with the coordinates as 0, 0, and then we'll keep on calculating the right one and the down one. Then this one will call it separate down one and the right one. Then this one will call its right one and down one. So if you see, this cell is being calculated twice, one for this above one and one for its left one. So that's why we are using DP, because there is an overlapping subproblem for calculating the unique path for this particular cell, this one. So what we can do is we can maintain a DP table that we discussed earlier, and it will help us to pre-compute, not exactly pre-compute, to like compute just once and reuse it any number of times that whenever we encounter this cell. So I hope we have discussed all important things like the state, the transition, and the base cases, as well as some out of bound errors. So let's go towards the code part. Yeah. So here's the code part. I don't know why. Okay, so this was the starting function that we had, the unique path, and it gave us two coordinates m and n, the sizes of the grid. And then what we did is we created our DP table, and then we call the function, our helper function. We named it as DFS. You can call it anything as you want. So what we are passing DP and the initial coordinates. You can also do like, you can just make DP outside the function, make it a global variable, assign it memory in the main function of unique paths, and just use it there. It's as per you. We prefer passing it directly into the function. And now we describe the function as DFS with the DP table and I and j coordinates of the cell. So if I and j, either one of them goes out of bound, that is out of from the DP dot size, that is from the row side or from the column side that we discussed, these these part. If it ever hits a cell over here, it's gonna return 0. And for the case where both of these are the very end, then it's gonna return 1. Also one thing, if dpij has some value, say 2 unique path, 3 unique paths in the state, we are simply going to return them. We are not going to calculate it again. And if we have never calculated it, we are going to simply return DFS for the right path that we had. And DFS for the bottom part, and store it inside dpij. So let's try to run this. Yeah, accepted, and now we'll submit. Both the test cases were passed. Yeah, and it gave us 100% runtime. So yeah, I hope you understand. Now you can think of like how to go for a DP solution. We might bring a detailed video on DP in case you had doubts like how to calculate states, how to identify whether to use a 2D DP or 1D DP, or like how to find the transition, how to find the base case or the edge cases. So in case you have any doubt, you can just drop them in the comments. And this is just for the this is for this video, and we'll come in the next video with another question of unique path second. Thank you.